Actually, oh yeah, I'll show you this first. So we left off talking about reaction orders, but I didn't think the simulation would actually work on here, but it does. It's super old. Well, not the rate experiment, this one. Yeah. So we had some of those. We had some of these. They bounce around. And this is like, you know, super simplified version of, I can't zoom on it at all. Super simplified version of what you should be thinking about when you're thinking about a chemical reaction, right? And right now, actually, we don't have anything reacting. And that's because of something that we'll talk about later, which is the activation energy. So I have to actually increase the temperature on this enough so we get collisions with enough energy that they end up reacting. All right, so you need energy and you need them to collide in the correct way. This is a really old simulation, so it is a little bit janky. Anyways, reaction orders. So let's see where we gas chromatograph. Yeah. So I have zero order, first order, second order. There can be other orders. There can even be fractions. So it's not always going to end up being a whole number. I think fractions are relatively rare. Ask me later if you're curious about like, well, how can we get a fraction based on most of these things? It seems like whole number orders make more sense. Fractions are a little bit weird. It's when you've got a bunch of reactions happening at the same time. So we saw these rates. So as a reaction proceeds, you'll notice different things about the rate of the reaction as time goes on. So for a zero order reaction, the rate doesn't change. First order, it does change. In second order, it changes more. We never really quantified those things. Then actually, this is where I have to go back and I have to actually correct this lecture video because I said that radioactive decay was zero order. It is not. It's first order. Zero order, the rate changes, or actually, we'll talk about in terms of half-lives, but zero order would be something like, even like an ice cube melting, or in this case, if it was dry ice, subliming. And we'll see why when we talk about half-lives, how that's different. We already went through these, right? Yeah, okay. I was like, yeah. Oh yeah, this is where we were. Determining the reaction order from actual data. So we're looking at any given chemical equation, chemical reaction. We can't use that to determine the reaction order. There could be other things going on. The overreaction doesn't really tell us what's happening, but we have to do an experiment to figure out from rates and how the rate changes as a function of either initial concentrations and initial rates or changes over time. So here we have concentrations increasing of one of our reactants, and we also get initial rates. We can see that those are also increasing. So for a simple reaction like this one, we can look at these, and really what you're looking for is anytime something doubles, right? Because if it doubles, so like here, that's a 2x in concentration. And then if we go and we look at the rates, the rate goes from 0.015 to 0.03. So it doubles also. So that's also a doubling or a 2x increase in rate. And that's really all of the information that we need, but we can reinforce it by saying, like, if we go from 0.2 to 0.4, that's also a 2x. And if I look at the rate there, that also increases by 2x. So what order of reaction would this be? First order. If it was zero order, rate wouldn't change. If it was second order, doubling concentration would quadruple the reaction rate. So since we get a 2x increase in concentration, 2x increase in rate, then we can just say this is first order. Now to determine the rate constant, we have to pick some of these numbers and use them and actually calculate what that rate constant is. I need to remind myself of the first order equation. Yeah, so equation is the rate equals K, which is our rate constant, times the concentration of one of the reactants. And in a first order, that's raised to the first power. So rate is equal to K times concentration of A. And because we determined already that it's first order, the exponent that we're raising A to is also 1. And it doesn't matter which of these data points we use, right? Because it's the rate constant, because it's constant for that reaction, regardless of any of the concentrations. I don't think any of them are necessarily easier in this case, but initial rate 0.015 molar per second, K, and then we're solving for, or well, we can also plug in that. And so divide, which should just be 0.15. Yeah. So 0.15. Oh, and actually, this is molar. Yeah, so actually, I want to write this out because so I'm dividing by 0.1 molar. Here I'm dividing by 0.10 molar. What do the units end up being? Yeah, the molars cancel. So it ends up being 1 over seconds. Or as you'll see written in the book and other places, S seconds to the minus 1 equals K. So the important thing when you're trying to determine what K is using you need to know what order of reaction it is first. Because obviously for every different order, you're going to get different answers because the equation for the rate is different. Sometimes the rate is not super obvious. So like these ones are nice and obvious. Oh, didn't mean to do that. So our concentrations here, again, doubling. But again, if we had seen them stay the same, that would be 0 order on the initial rate. Here, again, I got the 2x, but 0.015 to 0.06, that's a 4x. But the thing that we can do is if we can't tell immediately, right, if we can't do this, well, is this concentration doubling? Is this quadrupling, doubling, staying the same? Obviously, staying the same would be pretty easy. But if it's not easy to determine, then we can set up 2 of these data points. So for example, actually, yeah. For example, if I took the rate, let's make this rate 2 and make this rate 1, then I would do 0.060 divided by 0.015 equals K over K. And then concentration for 2 is 0.20. Concentration of 1 is 0.10 to the N. Now, one of the things we can do to simplify this, and we'll do like an actual calculation in a bit, but the K is a constant. So for the same reaction, K is going to be the same thing. So I can immediately just cross that out from both of these and solve for N. I'm not going to go through that on this one because we know it's going to be 2, but we will see one in a little bit where it's not immediately obvious what the rate is or what the reaction order is. So we did for the first order rate. Rate is always moles per second, or sorry, moles per second, molar per second. And the concentration is always going to be molar. But because we have these exponents involved in the rate equation, that's either going to in the case of a zero order, n to the 0 power is going to be 1. So this drops out. In the first order, it ends up just being molar. This would be molar to the first. In the second order, it ends up being molar squared. But that doesn't match what the rate is supposed to have units of molar per second. So you could just memorize for each of these orders of reaction what K's units are. But I think the much easier way to do it is to look at the equation and say, well, I need to end up with units of molar per second. And K will have whatever units it takes to make my final units molars per second. So if we look at the zero order, I need to get to molar per second. My molar from the concentration of that reactant is gone because that was raised to the 0 power. What are the units of K? If I don't have any units now because of this, right, those units are now gone. What units does K have to be molars per second? Molar per second, yeah. So this is molar per second. So for a zero order reaction, the units of K is molar per second. For the first order reaction, now I've got molar on the right side. What unit of K do I need to make it molar per second? Yeah. Right here I'm missing something, and it's the 1 over seconds. So now 1 over seconds times molar will give me molar per second. And then for the second order rate,
1 over second squared. 1 over second.
Yeah. So I got to get rid of, yeah, you could do the square root of 1 over second squared. Oh no, you have to square root it afterwards. But yeah, if we just, as simply as possible, if I put a molar in the denominator here and a seconds in the denominator, right? We're really just canceling out the units to get to whatever it is. And so the 1 over seconds is always present because the concentration is never going to have that. The thing that we need to correct for is getting rid of extra units of molar, in a sense. So just to reiterate, here's going to be molar per second. Here's going to be 1 over seconds. There's going to be 1 over molar seconds. If I had a third order, right, then it'd be rate equals K times A to the third. I still need to get to molar per second. So what would my units be for K? I got to get rid of 2 of those units of molar. So it's molar squared seconds. You'll also see these written as molar seconds to the -1, seconds to the -1, molar to the -1, seconds to the -1. Because -1 really just puts it in the denominator. Cool. So again, you can just memorize them, but if you remember this is a method for figuring it out every time. All right, so we have a reaction, A to B, determined to be second order, so we're just given that. That's nice. The initial rate is 0.01 molar per second. Initial concentration of 0.1 molar. If I increase the concentration to 0.5 molar, what will my new initial rate be? might help to see it more as a table. Oh. How much does my initial concentration increase by? 2 times, 3 times, 5 times. Right, so if this increases by 5x, if this was a first order, then my rate would increase by 5x. But it's not a first order, it's a second order. So how much would my rate increase by? Yeah. See what you're thinking? So, and if you think about it like this, right? If I had a 2x and it's second order, then I would get an increase of 4x. If it was 4x, I would get an increase of 16x. It increases by the square. So 5x means that this needs to increase by 25 times 5 squared. And that ends up being 0.250 molar per second. That's not the only way to solve this problem. Wait a minute, right? It's not the only way to solve this. We could set this up because we know the rate. We could set this up as the rate is equal to K concentration of A squared. And because we have an initial rate and we have an initial concentration, we could figure out what K is. And then once we have K, we could plug in our new concentration and figure out what the new rate is. And I do like problems where there's 2 ways to solve it, because this is a problem that the intent is that you just look at the increase in concentration, you know it's second order, so you know that it's going to increase by the square of the increase of the concentration. And if you know those things, you don't have to say them all out loud, you can solve this problem a lot faster. But there is another way that if you know how to solve for things in equations, then you could just solve for it with the math. Questions? Good? Right. So we've been looking at very simplified versions of the rates where we only have a single reactant. Most of the time you have more than one reactant. And again, the rate order has to be determined by experiment. I can't really draw any information from my equation. The balanced chemical equation, that is. So when we have multiple reactants that affect the rate of the reaction, we have rate orders with respect to each of those reactants, and then we have a rate order with respect to the overall reaction, which is where you just add up those exponents. Because they're being multiplied, right, add exponents. So our overall rate order here would be m plus n. As a great example of this, so first equation here, you should always be looking for patterns, but be aware when those patterns don't mean anything. So here, for example, I've got coefficients of 1. It is complete coincidence that the exponents here are also 1. It's just a coincidence. So the rate order of this with respect to hydrogen would be first order because it's to the first power. It would be first order with respect to iodine. The overall rate would be second order. Just adding those exponents together. And as an example of why it's just coincidence in the first one, if we're looking at the second reaction, I have coefficients of 2 for hydrogen and 2 for nitrogen monoxide. But when we look at the rate, hydrogen is still first order. Nitrogen monoxide is second order. So with respect to hydrogen, that's first. This is second. So the overall rate order is, third order. Am I going too slow? No? I think some nods. Some people shake their head. Okay. It's one of those things. It's been a long time since I taught Chem 2, so the pace, still feeling out. Okay, so if we have a reaction like this one, we want to determine the rate order with respect to each of our reactants, and then also determine the overall rate order. The way you do this experiment is you change the concentration of one thing at a time. So my experiment would be, and actually you'll be doing this experiment not exactly next week, but the week after is where you'll really be doing this experiment and you're changing specific concentrations. We'll get a feel for it next week. So on this data table, right, we've got it's not methylene chloride, it's chloroform and chlorine. And in these first two reactions, they changed the concentration of the chloroform. They did not change the concentration of the chlorine. Because if we change both at the same time, then we've got two things going on at the same time, and we don't know where the effect is coming from. But by changing just one, I know the only difference is this changing concentration. So whatever the change in the rate is has to be because of what I changed, at least in theory. So if this increases by 2x, how much does my initial rate change by? Just about 2x, yeah. And this is where experimental data versus, or I guess like theoretical data versus real experimental data is going to have a little bit of error, right? It's not exactly 2x, but we also don't know if this number was 0.35, maybe it's, 0.00345, in which case we get 0069. So there's going to be a little bit of error, but that's really, really close to being double. So this is also a 2x. So with respect to chloroform, what's the order of the reaction? First, right? If one doubles, the other doubles, then that's first order. So for chloroform, let's do it this way, Cl3 is going to be, this way, is going to be first. So now I got to go back to our data and look at for chlorine. We need to find a place where the concentration of now chloroform stays the same, but chlorine changes. And really there's only one spot where you can do that, because here, right, for these two experiments, chloroform stayed the same, but the chlorine concentration was changed. And again, this is 2x. But what is 0.0098 or 0.0069 up to 0.0098? It's not 2x, it's about 1.5. Yeah. Actually, how close to 1.5 is that? It is, it's 1.42. This is 1.420x. So it could be that it's 1.420. It could be that there is a little bit of experimental error here that's making it not exactly 1.5. But this is not the only way to determine. We could use that equation where we have rate 2 divided by rate 1. We're basically dividing one rate equation by the other. And this should be K times the concentration, the n, k times the concentration, the n. This is going to be for 2 and for 1. And again, we can drop k and just use these rates. 0.0098 over 0.0069 concentration. Oh, wait, we can fill that in. 0.02, 0.01. That's raised to the n. This is raised to the n. And then solve for n. So testing your algebra skills here a little bit. The rate order should be the same for both of them, right? For both equations. So we can actually take this and change it to actually, let me divide those on the left side. That'll be divided by 0.0069. So that's that 1.42. Equals, and I can take this and I can do 0.020. And I can pull that n sort of out and say both of these divided by, or to the power of n. And then that becomes 2 raised to the n. How do we solve for n? Log. So take the log of both sides. This becomes log 1.4203 equals n log of 2. So now the log of 1.42 divided by the log of 2 Yeah. 0.50618 or so. That's a lot closer to sort of a whole fraction than 1.42. So this is saying that our order actually, this equals n, is actually 1/2. And there really is a lot that you can do. I mean, there's a lot you can do to simplify that equation just from the outset, but then you have to memorize it. So then our rate with respect to chlorine is 1/2. So then a rate equals K times CHCl3 to the 1 times Cl2 to the 1/2. So if we want to find K, then we just pick one of these lines of data to plug in and solve for K. 0.0035 equals so 0.0035 divided by that divided by 0.01 to the 1/2. That should be it. Oh yeah, units. Yeah, so if our overall rate is, or overall order is 1.5, then that's 1.5 molar. So then I need this to be molar to the negative 1/2. I think that's just supposed to be seconds to the negative 1. And not seconds to the negative 1/2. Questions? Everybody good? Feel free to ask later if you have questions about algebra. Me or Omar or Jonathan. Okay. That was a bunch of math. So if we have this reaction that's determined to be first order with respect to oxygen, second order with respect to nitrogen monoxide, I have a diagram that represents the mixtures in which the number of each type of molecule represents its initial concentration. Really, we're asking which one is faster, A, B, or C. And we could write out that we know our rate is going to depend on the concentration of oxygen to the first and the concentration of nitrogen monoxide to the second. Because we're told second order with respect to nitrogen monoxide, first order with respect to oxygen. So which concentration matters more for the rate?
Nitrogen.
Nitrogen monoxide, right? Higher order. Yeah, and then you just got to go through and say, well, this is 3, this is 2, this is 4 nitrogen monoxide. So the one with the highest concentration of nitrogen monoxide will also have the highest rate.
Ah.
All right, and that's where we were supposed to get to on Wednesday. Roughly. Because now we're going to talk about taking these rate laws and integrating them. But don't worry, you don't have to do any actual calculus. Or I'm sorry if you really were looking forward to calculus. We won't be doing any. So really before, we're just looking at the relationships between rate of reaction and concentration of a reactant. The integrated rate law gives us the relationship between the concentration and time. So we're integrating these all with respect to time. And when we take that, when we do that integral, and we integrate this with respect to time, it lets us actually predict the concentration of products or reactants in the future. So beyond whatever our experiment did, because the rate that the rate changes is constant. So it's slowing down at a specific rate. So our first order integrated rate law, start with the differential rate law. And really, whenever we see rate, remember we talked about units of K. The units of K have to be whatever it takes really to get our rate to be molar per second. And that's because it's the change in concentration divided by the change in time. And for a reactant, that'll be negative. And then when we integrate this from basically the concentration at time 0 to time t, that changes to the natural log of the concentration of A at time t equals negative kT plus the natural log of the initial concentration. That's annoying. And then this essentially, well, it becomes a straight line. And with straight lines, it's really easy to predict where that straight line is going to be in the future. A little bit of rearranging and we can get this other version. And what this tells us is that if we take actually the natural log of our concentrations and we just plot those on a graph according to time, we get that straight line where the slope of that line is at least negative k. The negative is part of the equation. K is going to be positive. So it's really like I'll do it over here. Slope equals negative k. Just to show the negative is part of the equation. K is positive. Yeah. So if we then are able to plot out more data, maybe we've got an automated way to monitor the concentrations over time. We can set up an experiment, collect a whole bunch of data, plot the natural log of the concentration according to time. And as we'll see, whether or not it's the natural log or the natural log is specific to first order reactions. When we plot this, so we've got all this data, and the plot, the graph, when we plot that natural log of the concentration, gives us a straight line, the slope of which is k. So my rate constant then, k, is equal to 0.000290, and this is first order, so it's 1/seconds. So you can just read it off the graph, just know k is positive. The negative is part of the equation. So now with an integrated rate law, we can predict if we did let this reaction go on into the future, what would the concentration be after 1900 seconds? So now we need this new equation, which is the natural log of, this will be SO2Cl2 negative KT plus the natural log of the initial concentration. One of the things that's easy to miss is that when we're plugging in this information, I can get K, that's the 0.00290, and that's in 1/seconds. That's times 1900 seconds plus what? What is my initial concentration of SO2Cl2? 2.30. A little bit weird though, right? Because it's negative 2.30. It's negative because we can't have a negative concentration. It's not possible. You can't have less than nothing. The reason it's negative 2.30 is because this intercept and the y-axis are not for the concentration, it's for the natural log of the concentration. So what you might miss is that you might look here, even though, I mean, it does give you the y-intercept here, but you might look up here and say, oh, the concentration is negative 2.3 or 2.3, and then you plug in the natural log of 2.3 to do this whole equation, but it's already the natural log. So really we're just plugging in negative 2.3. The natural log part of that has already been done. So to solve, it's just math. Times 1900 minus 2.3. I don't have the right number of zeros there. Yeah. So we get the natural log of actually, I'm not going to bother with units because the units are going to be weird. So now we got to undo that natural log, which means use the natural base. So E, well, on this side, it's E raised to the negative 2.851. So the concentration of SO2Cl2 is 0.0577. Actually, I think we only have 2 sig figs. Oh, we do have a 0 there. Okay. Yeah. So 2 sig figs. That looks like a micro. Nobody's going to ask why 2 sig figs. When you take the natural log of something, or you take the log base 10 of something, the first number, the number before the decimal, does not count for sig figs. So like this 2 doesn't count for sig figs. And that's just because of the way the logs work. That log, when you take the log of something, like if we did the pH, right? You take the log base 10. That exponent part becomes the first number in the natural log of something. So if I did the natural, or if I did the log base 10 of 10 to the negative 4, that equals negative 4. And if you think about this in terms of like, well, that 10 to the negative 4 is kind of like scientific notation, right? We don't use the exponent part of scientific notation for sig figs. So it's the same thing here. The exponent gets packaged as the numbers before the decimal. And it's only the number after the decimal in a log. Probably bring this up. I don't know how much Alex is going to be a stickler for this. I do have the check. It is? Okay. I did check the thing where it's like, check your sig figs, where it'll tell you to check your sig figs. Like it won't tell you what the sig figs are supposed to be, but it will like give you a reminder before telling you that you're just wrong. Yeah, I can go over more examples of that another time, but suffice it to say here, this is the log, natural log of the concentration. So then this number is only 2 sig figs. So final answer should have 2 sig figs. Any questions? No? Guys are real quiet. Oh yeah. So cyclopropane arranges to form propene in the gas phase. The reaction is first order in cyclopropane. It has a measured rate constant of 3.36 times 10 to the negative 5 seconds, 1 over seconds, at 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what will it be after 235 minutes? So if this didn't tell us that it was first order already, then the rate constant units tell us that it's first order. And again, remember, it'll be whatever units it needs to be to make the overall rate molar per second. And And because we're predicting something in the future, we need to use the integrated rate law. I'm going to give these letters. We're going to call this C. Actually, let's call it CY. And then that'll just make things easier to rate. 6 times 10 to the negative 5 times T plus natural log of my initial concentration, 0.0445 molar. Oh, I didn't write the units. Shame on me. So I didn't write T in there. Why didn't I write T in there? Got to convert minutes to seconds. I got to convert minutes to seconds because my rate constant has units of 1/seconds. So 235 times 60. So it's going to be 14,100. Now those are both seconds plus, oh, and here's a good example. So 0.0445, how many sig figs is that? 3. Start at the first non-zero number and then count from there. So that's 3 sig figs. If I take the natural log of that, I get negative 5.41485118. How many of those would be significant? The first 3 after the decimal. So I start here, the 414, those are significant. So that's still 3 sig figs. But because I took the natural log, anything before the decimal is not significant or doesn't get counted for sig figs. Now we kind of just solve. So that plus negative 3.36 e to the negative 5 times 14,100. So this is still the natural log of cyclopropane. 653399896. Still 3 sig figs. And now I got to do E raised to that. Oh, I messed something up. Wait. Oh, I see what I did. It's like, how did this end up positive? Negative 3.36 e to the negative 5 times 14,100 plus a negative 5.414851183. Oh, maybe I just had the sign wrong. 5.8886. Really, only these 3 are significant. There we go. And then it's E raised to that as a power. So then 0.00277. Yeah, because it's 3 sig figs. Well, that's as good a stopping place as any. Any questions? I got to go fast through the math because I was expecting to be on like slide 72 or something today. That's okay. We'll figure it out.